Imagine you're holding a flashlight in a speeding train. Common sense tells us that the light should travel faster than normal. The flashlight's speed plus the train's speed, right? Not exactly. No matter how fast that train moves, whether it's crawling at 1 mile per hour or screaming along at half the speed of light itself, the beam from your flashlight will always travel at exactly 299,792,458 meters per second. Not a second faster and not a whisper slower. Today, we're diving deep into one of nature's most profound mysteries. Why is the speed of light the ultimate barrier that shapes everything, from the smallest quantum particles to the largest structures in the cosmos? If you're fascinated by the fundamental laws that govern our universe and want to explore more cosmic mysteries, make sure to subscribe to this channel and give a like. And here's something I've been pondering. If you could break just one law of physics for a day, which would it be and what would you do first? Share your rule-breaking dreams in the comments below. I will pin the most creative answer. Now let's begin. To understand why light speed is the universal limit, we need to journey back to 1905, when a 26-year-old patent clerk named Albert Einstein published a paper that would revolutionize physics forever. His special theory of relativity wasn't born from complex experiments or advanced mathematics. It emerged from a simple thought experiment about chasing a beam of light. Einstein imagined what would happen if he could run alongside a light wave at the same speed. Would he see a frozen wave of light suspended in space? This seemingly innocent question led to a shocking realization. Such a scenario was impossible because it would violate Maxwell's equations, which showed that electromagnetic waves must always propagate at a constant speed. But Einstein's insight went deeper than just the behavior of light. He realized that if the speed of light is constant for all observers, whether you're standing still or moving at tremendous velocity, then our basic assumptions about space and time must be wrong. In Newton's universe, space and time were absolute, unchanging stages where events played out. Einstein showed that space and time are actually flexible, interconnected, and relative. They stretch and compress depending on how fast you're moving, always conspiring to keep the speed of light constant. The experimental evidence for this cosmic speed limit is overwhelming. In particle accelerators like the Large Hadron Collider at CERN, physicists routinely accelerate protons to 99.99999% the speed of light. Despite pouring in enormous amounts of energy, enough to power a small city, these particles never quite reach light speed. Each additional fraction of a percent requires exponentially more energy, approaching infinity as you near the ultimate barrier. It's as if the universe has built an impenetrable wall that gets infinitely high as you approach it. But why does this limit exist at all? The answer lies in the fundamental structure of space-time itself. When Einstein developed general relativity, he showed that space and time aren't separate entities, but aspects of a four-dimensional fabric called space-time. The speed of light isn't really about light at all. It's the speed at which cause and effect can propagate through this fabric. It's the maximum rate at which any change can ripple through the universe. Light just happens to travel at this maximum speed because photons have no mass. Think of space-time like a cosmic fabric with a maximum tension. Just as sound waves can only travel so fast through air because of air's physical properties, disturbances in space-time can only propagate at a certain maximum rate. This rate, the speed of light, is built into the very geometry of the universe. It's not a speed limit imposed from outside, it emerges from what space and time actually are at the deepest level. The consequences of this universal speed limit are profound and often counterintuitive. Time dilation, one of the strangest predictions of relativity, has been confirmed countless times. When GPS satellites orbit Earth at high speed, their clocks run faster than clocks on the ground, not because the clocks are malfunctioning, but because time itself flows differently. Without correcting for this relativistic effect, GPS would accumulate errors of about 10 kilometers per day, making navigation impossible. Even more bizarre is length contraction. Objects actually become shorter in their direction of motion as they approach light speed. If you could watch a spacecraft accelerate to near light speed, you'd see it compress like an accordion. From the perspective of someone on the spacecraft, it's the universe that contracts. At 99.9% light speed, the distance to the nearest star would shrink from 4.2 light-years to just a few light-months from the traveler's perspective. The mass-energy equivalence captured in Einstein's famous equation E equals mc squared reveals another facet of why light speed is the ultimate barrier. As objects accelerate, they gain kinetic energy. But Einstein showed that energy and mass are interchangeable. They're different forms of the same thing. As you pump energy into accelerating an object, that energy manifests as increased mass. The faster you go, the heavier you become, requiring ever more force to accelerate further. At speeds close to light, this effect becomes dramatic. A spacecraft traveling at 90% light speed would have more than double its rest mass. Speaking of the impossibility of reaching light speed, if you want to dive deeper into the practical barriers that make faster-than-light travel a pipe dream, check out my video, "This is why we will never reach the speed of light," where I explore the mind-bending physics and engineering challenges in detail. The link is in the description below and on the card above. Now let's continue unraveling why this cosmic speed limit exists in the first place. Recent observations from the LIGO and Virgo gravitational wave detectors have provided stunning confirmation that the speed of light truly is universal. When two neutron stars collided 130 million light-years away in 2017, the event sent out both gravitational waves and light. Despite traveling through the cosmos for over 100 million years, both signals arrived at Earth within 1.7 seconds of each other. This incredible observation proved that gravity itself propagates at the speed of light, just as Einstein predicted a century ago. But here's where things get philosophically deep. The speed of light limit isn't just about preventing fast travel, it's about preserving causality itself. Without this limit, cause and effect would break down. You could theoretically send information into the past, creating grandfather paradoxes where you could prevent your own existence. The universe seems to have a built-in protection mechanism against such logical contradictions, and that mechanism is the speed of light. Consider what happens at the quantum level. Virtual particles constantly pop into existence and annihilate in the quantum foam of empty space. These fleeting particles must also respect the speed of light limit. Quantum field theory shows that forces are transmitted by exchange particles, photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force. All these force carriers are constrained by the same universal speed limit, ensuring that no influence can propagate faster than light, even in the quantum realm. The Alcubierre drive, proposed in 1994, seemed to offer a loophole. By warping space itself, contracting it in front of a spacecraft and expanding it behind, you could theoretically travel faster than light without locally exceeding the speed limit. It's like moving the space around you rather than moving through space. But recent calculations show this would require exotic matter with negative energy density, something that may not exist in the required quantities. Even if it does, the energy requirements are staggering, equivalent to converting the mass of Jupiter entirely into energy. Quantum entanglement often gets misrepresented as faster-than-light communication. When particles are entangled, measuring one instantly affects the other, regardless of distance. Einstein called this spooky action at a distance and was deeply troubled by it. But here's the crucial point. While the correlation is instantaneous, no usable information can be transmitted this way. The universe seems carefully designed, to allow quantum weirdness while still protecting the speed of light as the limit for actual communication. The cosmic microwave background radiation provides another piece of the puzzle. This ancient light, released 380,000 years after the Big Bang, has been traveling through space for 13.8 billion years. Its properties tell us that the speed of light has remained constant throughout cosmic history. If light speed had varied even slightly over billions of years, we would see distortions in this primordial radiation. The fact that we don't suggests the speed of light is truly a fundamental constant woven into the fabric of reality itself. Tachyons, hypothetical particles, that always travel faster than light illustrate why the speed limit is so fundamental. If tachyons existed, they would have imaginary mass and experience time backward. They could never slow down to light speed, just as regular matter can never speed up to it. The mathematics of tachyons leads to paradoxes and violations of causality so severe that most physicists believe they simply cannot exist. The universe seems to forbid anything that would threaten the logical consistency of cause and effect. Recent experiments with neutrinos have repeatedly confirmed that even these ghostly particles, which barely interact with matter, still respect the universal speed limit. In 2011, the OPERA experiment initially reported neutrinos traveling faster than light, sending shockwaves through the physics community. But careful reanalysis revealed a loose fiber optic cable had caused a timing error. When corrected, the neutrinos were traveling at precisely the speed they should, just below light speed, as their tiny but non-zero mass requires. The relationship between the speed of light and the fundamental constants of nature reveals just how deeply this limit is woven into reality's fabric. The fine structure constant, approximately 1 divided by 137, determines the strength of electromagnetic interactions. This dimensionless number emerges naturally from the speed of light, Planck's constant, and the charge of an electron. If the speed of light were different, all of chemistry would change. Atoms would form differently, molecules would have different properties, and life as we know it couldn't exist. The Planck length and Planck time, the smallest meaningful units of space and time, are defined in part by the speed of light. At scales smaller than 10 to the negative 35 meters and times shorter than 10 to the negative 43 seconds, space and time themselves become fuzzy and quantum mechanical. The speed of light sets the conversion factor between space and time in these fundamental units. It's not just a speed limit for motion, it's a fundamental property of the dimensional structure of the universe itself. Modern cosmology reveals another fascinating aspect of the light-speed barrier. The observable universe has a radius of about 46 billion light-years, even though the universe is only 13.8 billion years old. How is this possible? Because space itself can expand faster than light without violating relativity. The speed limit only applies to objects moving through space, not to space itself stretching. Galaxies beyond a certain distance are receding from us faster than light due to cosmic expansion, and we will never be able to see them or communicate with them, no matter how advanced our technology becomes. The cosmic event horizon created by this accelerating expansion means that approximately 97% of the observable universe is already beyond our reach. Even if we could travel at the speed of light, we couldn't reach those distant galaxies because space is expanding between us faster than we could traverse it. The universal speed limit combined with cosmic expansion has essentially trapped us in our cosmic neighborhood. We're isolated by the very laws that make the universe comprehensible. Dark energy, the mysterious force driving cosmic acceleration, accounts for about 68% of the universe's total energy density. Discovered through observations of distant supernovae in 1998, dark energy's existence was confirmed by multiple independent observations, including the cosmic microwave background and large-scale structure surveys. Its presence means the observable universe is effectively shrinking. More galaxies cross the cosmic event horizon every day, becoming forever unreachable regardless of technology or time. Black holes provide the most extreme test of the speed of light limit. At the event horizon, the point of no return, space flows inward at exactly the speed of light. Nothing can escape because that would require moving faster than light relative to the infalling spacetime. The Event Horizon Telescope, which captured the first image of a black hole's shadow in 2019, showed us this boundary where the speed of light becomes insufficient to escape gravity's grip. Even light itself is trapped, making the hole truly black. The mathematics of spacetime geometry reveals why the speed of light is special. In special relativity, we describe motion through four-dimensional spacetime. When you're at rest in space, you're moving through time at maximum speed. When you move through space, you're converting some of that temporal motion into spatial motion. The speed of light represents the case where all your motion is through space, leaving none for motion through time. This is why photons don't experience the passage of time. From a photon's perspective, it's emitted and absorbed in the same instant, regardless of how far it travels. This space-time trade-off explains why nothing with mass can reach light speed. To reach light speed, all your motion would need to be through space, with none through time. But mass inherently ties you to the flow of time. Only massless particles like photons can achieve this complete conversion. Anything with mass would require infinite energy to reach the point where time stops flowing for it, which is physically impossible. The universe draws a bright line between massive particles that must always travel slower than light and massless particles that must always travel at light speed. Neutrino oscillations discovered in the late 1990s proved that neutrinos have tiny but non-zero mass. This discovery, which earned the 2015 Nobel Prize in Physics, means neutrinos must travel slightly below light speed. Before this discovery, scientists thought neutrinos might be massless and travel exactly at light speed like photons. The fact that they have mass, even just a few millionths of an electron's mass, means they're subject to the same universal speed limit as everything else with mass. The cosmic speed limit has profound implications for the search for extraterrestrial intelligence. Even if advanced civilizations exist throughout the galaxy, they're separated by vast distances that take years or decades to cross, even at light speed. A radio message to Proxima Centauri, our nearest neighboring star system, would take 4.2 years to arrive and another 4.2 years for a reply. For stars hundreds or thousands of light years away, conversations become impossible. The speed of light doesn't just limit travel, it limits the rate at which civilizations can communicate and share knowledge. The Pioneer and Voyager spacecraft, launched in the 1970s, are now in interstellar space, making them humanity's most distant ambassadors. But even these fastest human-made objects travel at only about 17 kilometers per second, less than 0.006% of light speed. At this rate, they would take over 70,000 years to reach Proxima Centauri, and they're not even headed that direction. The speed of light limit, combined with the vast distances between stars, creates an almost impenetrable barrier to interstellar exploration. Cherenkov radiation provides a fascinating exception that proves the rule. When high-energy particles travel through a medium like water, they can actually exceed the speed of light in that medium, but not the speed of light in vacuum. Light slows down in materials because photons interact with atoms, taking a zigzag path rather than a straight line. In water, light travels at about 75% of its vacuum speed. highly energetic particles can zip through faster than this reduced speed, creating a blue glow called Cherenkov radiation, visible in nuclear reactor cooling pools. This phenomenon is used by detectors like IceCube at the South Pole to study neutrinos from cosmic sources, but it doesn't violate the fundamental speed limit. Nothing goes faster than light in vacuum. The vacuum of space itself has properties that set the speed of light. Quantum field theory reveals that empty space isn't truly empty, but seethes with virtual particle pairs constantly appearing and disappearing. These quantum fluctuations give the vacuum an impedance, a resistance to electric and magnetic fields propagating through it. The speed of light emerges directly from these electromagnetic properties of the vacuum. It's calculated as 1 divided by the square root of the product of the vacuum's electric permittivity and magnetic permeability. Change these fundamental properties of empty space, and you change the speed of light itself. The Casimir effect demonstrates that the quantum vacuum has real, measurable properties. When two uncharged metal plates are placed very close together in a vacuum, they experience an attractive force. This happens because the plates exclude certain wavelengths of virtual particles between them, creating a pressure imbalance. The effect was predicted in 1948 and measured in 1997, confirming that the vacuum has structure. This structured vacuum is what constrains the speed of light. It's not propagating through nothing, but through something with definite properties. String theory, which attempts to unite quantum mechanics and gravity, suggests that space-time might be made of tiny vibrating strings at scales of 10 to the negative 35 meters. Even in these exotic theories, the speed of light remains special. It emerges as the maximum propagation speed for disturbances in the string field. Whether strings are fundamental or not, the mathematics consistently produces a maximum causal speed that matches our observed speed of light. The limit appears to transcend our specific theories and point to something deeper about the nature of reality. The holographic principle, emerging from black hole physics, suggests that the information content of any region of space is proportional to its surface area, not its volume. This bizarre result implies that our three-dimensional reality might be a projection of information encoded on a two-dimensional boundary. Even in this radical reimagining of reality, the speed of light remains the maximum rate at which information can propagate. It appears in the mathematical relationships between entropy, area, and information flow. The speed limit seems to be information theoretic in nature, not just mechanical. Quantum chromodynamics, the theory describing the strong force binding quarks into protons and neutrons, also respects the light speed limit. The gluons that carry this force are massless like photons and propagate at light speed. Inside protons and neutrons, quarks whiz around at nearly the speed of light, confined by the strong force. The Large Hadron Collider can accelerate individual protons to 99.9999991% of light speed, but never quite to light speed itself. Each additional 9 in that decimal requires dramatically more energy. The Lorentz factor, a mathematical expression in relativity, quantifies how time dilation and length contraction increase as you approach light speed. At 90% light speed, the Lorentz factor is about 2.3, meaning time runs 2.3 times slower. At 99%, it jumps to 7. At 99.9%, it reaches 22. As you approach 100%, the Lorentz factor approaches infinity, mathematically encoding the impossibility of reaching light speed. The universe uses infinity itself as a barrier. Recent precision measurements of the fine structure constant using atom interferometry have confirmed its value to better than 1 part in 10 billion. This constant, which depends on the speed of light, appears to be truly constant across space and time, and observations of distant quasars show that the fine structure constant had the same value billions of years ago as it does today. If the speed of light had varied over cosmic history, we would see changes in spectral lines from distant objects. The consistency of these observations tells us the speed limit has been constant throughout the observable universe's history. The cosmic microwave background's uniformity provides another confirmation. This radiation, released when the universe became transparent 380,000 years after the Big Bang, has the same temperature to within 1 part in 100,000 in all directions. This uniformity was puzzling until inflation theory proposed that a tiny region expanded faster than light in the universe's first fraction of a second. Space itself expanded exponentially, carrying matter and energy along with it. This inflation didn't violate the speed limit because it was space itself expanding, not objects moving through space. The inflationary epoch, lasting from 10 to the negative 36 to 10 to the negative 32 seconds after the Big Bang, expanded the universe by a factor of at least 10 to the 26. During this brief moment, regions of space separated faster than light could travel between them, solving the horizon problem. Why distant parts of the universe that could never have communicated have the same temperature? This cosmic inflation, driven by a hypothetical inflaton field, shows that while matter and energy respect the speed limit, space-time itself doesn't have to. The fabric of reality can stretch without bound, carrying everything embedded within it. Modern observations of type Ia supernovae, which serve as standard candles for measuring cosmic distances, revealed that the universe's expansion is accelerating. This discovery, which earned the 2011 Nobel Prize in Physics, means that galaxies are not just moving away from us, but doing so at an ever-increasing rate. Eventually, all galaxies not gravitationally bound to our local group will cross the cosmic event horizon, receding faster than light due to space's expansion. Future civilizations will see an increasingly empty universe, with fewer and fewer galaxies visible as cosmic acceleration continues. The Hubble constant, currently measured at about 70 kilometers per second per megaparsec, tells us how fast space is expanding. For every megaparsec, about 3.26 million light-years of distance, galaxies recede an additional 70 kilometers per second faster. At a distance of about 14 billion light-years, this recession velocity reaches the speed of light. Beyond this cosmic horizon, galaxies are already unreachable no matter what technology we develop. The speed of light combined with cosmic expansion has drawn an absolute boundary around our cosmic neighborhood. Wormholes, theoretical shortcuts through space-time, might seem to offer a way around the speed limit. General relativity allows for these exotic structures, which could connect distant regions of space through a higher dimensional tunnel. But maintaining a traversable wormhole would require exotic matter with negative energy density, something that may not exist in sufficient quantities. Even if wormholes could be created, recent research suggests they would be unstable, collapsing faster than anything could traverse them. The universe seems remarkably resistant to shortcuts that would violate the spirit, if not the letter, of the speed limit. The quantum Zeno effect demonstrates how observation itself can freeze quantum systems in place. By constantly measuring a quantum system, you can prevent it from evolving, essentially stopping time for that system. This bizarre phenomenon has been confirmed experimentally and has applications in quantum computing. It shows that at the quantum level, the flow of time, and therefore the meaning of speed, becomes fuzzy and observer-dependent. Yet even in this quantum realm, information cannot propagate faster than light. The speed limit holds even when time itself becomes uncertain. Loop quantum gravity, an alternative to string theory, suggests that space-time itself is quantized at the Planck scale. In this picture, space consists of discrete loops and nodes, like a fabric woven from individual threads. Time advances in discrete ticks rather than flowing continuously. Even in this radically different view of reality, the speed of light emerges as the maximum rate at which changes can propagate through the quantum foam. Whether space-time is continuous or discrete, smooth or grainy, the cosmic speed limit appears inviolable. The delayed choice quantum eraser experiment reveals just how deeply the speed of light is woven into quantum mechanics. In this mind-bending experiment, the decision to observe or not observe which path a photon takes can be made after the photon has already passed through a double slit. The photon seems to retroactively decide whether to behave as a wave or particle based on a future measurement. Yet despite this apparent retro-causality, no information can be sent backward in time. The speed of light limit protects causality even in the face of quantum weirdness. Cosmic rays, high-energy particles from space, provide a natural particle accelerator far more powerful than anything humans can build. The Oh My God particle, detected in 1991, had an energy of 3 × 10⁻20 electron volts, equivalent to a baseball thrown at 60 miles per hour, but compressed into a single proton. This particle was traveling at 99.999999999999995% of the speed of light. Despite this incredible energy, it still fell short of the ultimate barrier. The universe had accelerated this particle for perhaps millions of years, yet it couldn't quite reach light speed. The GZK cutoff, predicted in 1966, sets a maximum energy for cosmic ray protons traveling through intergalactic space. Above about 5 × 10⁻19 electron volts, protons interact with the cosmic microwave background, losing energy through photopion production. This creates an effective range limit of about 160 million light-years for the highest energy cosmic rays. The speed of light limit, combined with the cosmic microwave background, creates a cosmic ray horizon beyond which we cannot detect the universe's most energetic particles. Pulsar timing arrays are now searching for gravitational waves from supermassive black hole mergers. These waves, ripples in spacetime itself, propagate at exactly the speed of light. The Nanograv collaboration announced in 2023 that they had detected a gravitational wave background, a cosmic hum, from countless distant black hole mergers. These observations confirm that gravity, like light, respects the universal speed limit. Whether carried by photons, gravitons, or ripples in spacetime, all influences in the universe propagate at the same maximum speed. The speed of light connects to the deepest questions in physics. Why are there 3 spatial dimensions and 1 time dimension? Why do the fundamental constants have the values they do? The anthropic principle suggests these values allow for the existence of observers like us, but this feels unsatisfying. String theory predicts 10 or 11 dimensions, with the extra dimensions compactified at subatomic scales. Even in these higher dimensional theories, the speed of light in our familiar 4 dimensions remains the ultimate barrier. The limit seems to transcend the specific number of dimensions or the particular laws of physics. Quantum tunneling allows particles to pass through barriers that classical physics says should be impenetrable. An electron can suddenly appear on the other side of an energy barrier without having enough energy to climb over it. For many years, physicists debated whether tunneling was instantaneous or took time. Recent experiments have shown that tunneling does take time, and the process respects the speed of light. Even when particles take quantum shortcuts through barriers, they cannot violate the universal speed limit. The cosmos seems to have closed every loophole. The quantum eraser experiment takes the double-slit experiment to new extremes. By using entangled photons, scientists can choose whether to preserve or erase which path information after the photons have already hit the detector. The pattern that appears, interference fringes or not, depends on a choice made in the future. This seems to violate causality, but careful analysis shows no information travels backward. The correlations only become apparent when you compare results after the fact. Once again, the speed of light limit protects the logical consistency of cause and effect. Time crystals, first proposed in 2012 and created in 2017, are structures that repeat in time rather than space. These exotic states of matter oscillate perpetually without consuming energy, seeming to violate thermodynamics. But time crystals don't actually produce energy or allow faster-than-light communication. They're more like a loophole in the laws of thermodynamics that still respects all the fundamental limits. The speed of light remains inviolate even in these temporally periodic systems. The black hole information paradox highlights the tension between quantum mechanics and general relativity. When matter falls into a black hole, its information seems to be destroyed, violating quantum mechanics. Stephen Hawking proposed that black holes slowly evaporate through quantum radiation, but this radiation appears to be random, containing no information about what fell in. Recent proposals suggest information might be preserved in subtle correlations in the radiation or encoded on the black hole's surface. Resolving this paradox might require a theory of quantum gravity, but any solution must respect the speed of light limit. The holographic principle emerged from this black hole puzzle, suggesting that all the information in a volume of space can be encoded on its boundary. This means our three-dimensional reality might be equivalent to information on a two-dimensional surface infinitely far away. Even in this radical picture, the speed of light determines how quickly information can flow across this holographic boundary. The limit appears fundamental to information theory itself, not just to our particular universe. Whether reality is fundamentally three-dimensional or a holographic projection, the cosmic speed limit remains absolute. Dark matter, making up about 27% of the universe's energy density, remains one of cosmology's greatest mysteries. We know it exists from its gravitational effects on galaxies and galaxy clusters, but we've never directly detected a dark matter particle. Whatever dark matter is, WIMPs, axions, primordial black holes, it must respect the speed of light. Even invisible matter that barely interacts with ordinary matter cannot escape the universal speed limit. Gravitational lensing observations show dark matter behaves according to Einstein's relativity, bending space-time and affecting light paths just like ordinary matter. The Bullet Cluster, a collision between two galaxy clusters observed in 2006, provided stunning evidence for dark matter's existence. X-ray observations showed hot gas lagging behind the galaxies due to electromagnetic interactions, while gravitational lensing revealed that most of the mass had passed through unimpeded. This cosmic collision playing out over millions of years shows that even dark matter respects relativistic physics. The invisible mass creating those gravitational lenses cannot exceed the speed of light any more than the visible galaxies can. Quantum entanglement experiments have become increasingly sophisticated, with the 2022 Nobel Prize in Physics awarded for work proving that local hidden variables cannot explain quantum correlations. These experiments testing Bell's inequalities confirm that entangled particles maintain instantaneous correlations regardless of distance. Yet despite this spooky action at a distance, no usable information can be transmitted faster than light. The universe maintains a careful balance, allowing quantum correlations while preserving causality and the speed limit for actual communication. The quantum internet, currently under development, will use entanglement to create unhackable communications networks. But even these quantum networks won't enable faster-than-light communication. While entanglement can provide perfect encryption and enable distributed quantum computing, the actual transmission of meaningful information still requires classical channels limited by light speed. The universe seems designed to allow quantum weirdness for security and computation while maintaining the speed limit for actual messages. Closed, time-like curves, theoretical paths through spacetime that loop back to their starting point in time, are allowed by general relativity under extreme conditions. These could exist near rotating black holes or in universes with specific geometries. But every proposed mechanism for creating usable time loops requires exotic matter or energy conditions that probably don't exist. Even if time travel were possible, the Novikov self-consistency principle suggests the universe would conspire to prevent paradoxes. The speed of light limit works hand in hand with other physical laws to maintain causality. The chronology protection conjecture proposed by Stephen Hawking suggests that the laws of physics prevent time travel on macroscopic scales. Quantum effects would destroy any would-be time machine before it could operate. Virtual particles would circulate through the time loop, gaining energy with each cycle until they destroyed the apparatus. The universe seems to have multiple fail-safes against violations of causality, with the speed of light being the first and strongest defense. Metamaterials with negative refractive index can make light appear to move backward, creating invisibility cloaks and other exotic effects. These materials manipulate the phase velocity of light, the speed at which wave peaks move, which can exceed c or even be negative. But the group velocity, the speed at which information travels, always remains below the speed of light. Even when we engineer materials that seem to break the rules, the fundamental limit on information transfer remains intact. The Unruh effect predicts that an accelerating observer will see empty space filled with warm radiation. From the perspective of someone accelerating at enormous rates, the vacuum itself glows with thermal energy. This effect, related to Hawking radiation from black holes, shows that the concepts of particles, energy, and even empty space depend on your state of motion. Yet throughout these radical shifts in perspective, the speed of light remains invariant. It's the one constant that all observers, regardless of their motion, agree upon. Tachyon condensation in string theory suggests that if faster-than-light particles could exist, they would be unstable, quickly decaying into ordinary particles that respect the speed limit. The vacuum itself would readjust to eliminate these superluminal particles. It's as if the universe has an immune system that removes anything threatening the integrity of causality. The mathematics consistently shows that any attempt to introduce faster-than-light particles leads to instabilities that eliminate them. The cosmic censorship hypothesis proposes that singularities, points where physics breaks down, are always hidden behind event horizons. We can never see a naked singularity where the known laws of physics fail. This principle, if true, means the universe protects itself from paradoxes and inconsistencies. The speed of light plays a crucial role in this cosmic censorship, ensuring that regions where physics might break down are forever hidden from outside observers. Variable speed of light cosmology, proposed as an alternative to inflation, suggests that light might have traveled faster in the early universe. This could solve the horizon problem without requiring an inflationary epoch, but even these theories don't really change the fundamental speed limit. They change the relationship between space-time and matter in the early universe. The causal structure of space-time still has a maximum speed. It's just that the conversion factor between space and time might have been different. Most cosmologists remain skeptical, as changing the speed of light would affect all of physics in ways that should be observable. The trans-Planckian problem in cosmology asks what happens when we trace quantum fluctuations back to the inflationary epoch. During inflation, today's largest cosmic structures originated from quantum fluctuations smaller than the Planck length. At these scales, our theories of physics break down completely. Resolving this paradox might require a theory of quantum gravity, but any solution must respect causality and the cosmic speed limit. The universe seems to maintain consistency even at scales where our current understanding fails. Quantum gravity theories like loop quantum gravity and string theory attempt to unify general relativity with quantum mechanics. Despite their radically different approaches, discrete versus continuous spacetime, point particles versus strings, both theories preserve the speed of light as a fundamental limit. This convergence suggests the speed limit is more fundamental than our specific theories. It's not just a feature of Einstein's relativity, but something deeper about the nature of causality and information. The firewall paradox proposed in 2012 suggests that black hole event horizons might be surrounded by high-energy firewalls that destroy anything falling in. This would resolve the information paradox but violate Einstein's equivalence principle. The debate continues, but any resolution must respect the speed of light. Information cannot escape from beyond the event horizon, because that would require exceeding light speed. The cosmic speed limit is central to the paradox and must be part of any solution. Emergent gravity theories propose that gravity isn't fundamental, but emerges from more basic quantum information processes. In Eric Verlinder's theory, gravity arises from changes in entropy and information. Even in these radical reconceptions where space-time and gravity are emergent rather than fundamental, the speed of light appears as a maximum rate of information processing. The limit seems to be information theoretic rather than mechanical. It's about the maximum rate at which reality can update itself. The quantum speed limit sets a minimum time for quantum systems to evolve from one state to another. This fundamental bound, related to the uncertainty principle, means that even quantum processes cannot happen instantaneously. The universe has a maximum rate of change built into its quantum mechanical foundations. This quantum speed limit is intimately connected to the relativistic speed limit. Both emerge from deeper principles about information, causality, and the structure of spacetime. Cosmological horizons create absolute boundaries in our universe. The particle horizon marks the limit of the observable universe. We cannot see beyond it because light hasn't had time to reach us. The event horizon marks regions we can never observe, no matter how long we wait, due to accelerating expansion. The Hubble horizon marks where recession velocities equal light speed. These overlapping horizons, all determined by the speed of light, define the boundaries of what we can know about the cosmos. The multiverse hypothesis suggests our universe might be one of countless others, each potentially with different physical constants. In some universes, the speed of light might be different, fundamentally altering physics and chemistry. But even in multiverse theories, each individual universe must have some maximum causal speed to maintain consistency. Without a speed limit, cause and effect break down, making a coherent universe impossible. The anthropic principle suggests we naturally find ourselves in a universe where the constants, including light speed, allow for stable atoms, chemistry, and ultimately, observers like us. Brain-world scenarios in string theory propose that our universe is a three-dimensional membrane floating in higher dimensional space. Gravity can leak into these extra dimensions, potentially explaining why it's so much weaker than other forces. But even in these exotic theories, the speed of light on our brain remains the ultimate limit for matter and information confined to our dimensional slice. The cosmic speed limit seems to be a feature of causality itself, transcending the specific number or arrangement of dimensions. The information loss paradox in de Sitter space presents another puzzle. Our universe is approaching de Sitter space, a maximally symmetric spacetime dominated by dark energy. In such a universe, event horizons surround every observer, and information can be lost beyond these horizons. This raises profound questions about the nature of reality and information. Yet throughout these conceptual challenges, the speed of light remains the constant that defines these horizons and limits how information can flow. Quantum error correction in nature might explain why the macroscopic world seems classical despite being built from quantum components. the universe might constantly perform error correction, suppressing quantum superpositions through environmental decoherence. This natural error correction happens at light speed, the maximum rate at which different parts of a quantum system can communicate and correct errors. The speed limit isn't just about motion, it's about how quickly nature can process and correct quantum information. The ER equals EPR conjecture, proposed in 2013, suggests that quantum entanglement and wormholes are the same phenomenon described in different languages. Every pair of entangled particles might be connected by a tiny wormhole. If true, this would deeply connect quantum mechanics and general relativity. But even these microscopic wormholes wouldn't allow faster-than-light communication. The universe seems carefully designed to allow quantum correlations while preserving the prohibition on superluminal signaling. Causal dynamical triangulation, an approach to quantum gravity, builds spacetime from tiny triangular building blocks. Computer simulations show that this approach naturally produces a universe with 3 spatial dimensions and 1 time dimension at large scales. The speed of light emerges as the maximum rate at which changes can propagate through this triangulated spacetime. Even when we build spacetime from scratch using completely different principles, the cosmic speed limit appears. The soft hair theorem proposed by Hawking, Perry, and Strominger in 2016 suggests that black holes might preserve information in subtle patterns on their event horizons. This soft hair, quantum patterns that store information about what fell in, could resolve the information paradox, but retrieving this information would still be limited by light speed. You'd need to collect Hawking radiation for billions of years to reconstruct what fell into the black hole. The speed limit ensures that information, while preserved, remains practically inaccessible. Analog gravity experiments use flowing fluids, or Bose-Einstein condensates, to simulate black holes and test predictions about Hawking radiation. These systems have their own maximum wave speeds, the speed of sound in the medium, that play the role of light speed. Remarkably, these analog systems exhibit many of the same phenomena as real black holes, including event horizons and thermal radiation. This suggests that the physics of horizons and the role of a maximum speed are universal features that transcend the specific system. The quantum null energy condition places constraints on how energy and matter can be distributed in spacetime. This principle, which emerges from quantum field theory, prevents the exotic matter distributions needed for traversable wormholes or warp drives. It's another way the universe protects causality and maintains the speed limit. Even quantum mechanics, which allows so many strange phenomena, conspires to prevent violations of the cosmic speed limit. Superluminal motion in astronomy appears to show jets from quasars and other cosmic objects moving faster than light across the sky. This is an illusion caused by projection effects. The jets are moving toward us at nearly light speed, causing their apparent transverse motion to seem superluminal. Careful analysis always reveals that nothing actually exceeds light speed. These observations actually confirm special relativity rather than violating it, showing how motion near light speed creates surprising visual effects. The Shapiro delay demonstrates how gravity affects the speed of light. When light passes near a massive object like the Sun, it takes longer to travel than it would through empty space. This isn't because light slows down locally, it always travels at c locally, but because space-time itself is curved, making the path longer. This effect has been measured precisely using radar signals bounced off planets and by observing pulsars in binary systems. It's another confirmation that gravity and the speed of light are intimately connected through the geometry of space-time. Primordial gravitational waves from inflation would carry information about the universe's first moments. These ripples in spacetime, if detected, would have been traveling at light speed for 13.8 billion years. The Bicep Array at the South Pole searches for their signature, in the cosmic microwave background's polarization. Whether or not these primordial waves are found, their speed is not in question. Gravitational waves, like light, propagate at the universal maximum speed. The vacuum birefringence effect, predicted by quantum electrodynamics and potentially observed near neutron stars, shows that extreme magnetic fields can affect light's propagation. In these intense fields, the vacuum itself becomes birefringent, splitting light into two polarizations that travel at slightly different speeds. But this doesn't violate the ultimate speed limit. It's more like the vacuum gaining properties similar to a crystal. The local speed of light still represents the maximum causal speed. Frame dragging around rotating massive objects like Earth or black holes causes space-time itself to swirl. This effect, confirmed by the Gravity Probe B mission in 2011, means that space and time are not just curved by mass but can be set into motion. Yet even spinning space-time respects the speed limit. The dragging effect falls off with distance and cannot be used to create closed time-like curves or enable faster-than-light travel. The universe maintains its causal structure even when space-time itself is in motion. The cosmic web, the largest structure in the universe, consists of galaxy filaments separated by vast voids. Dark matter and ordinary matter flow along these filaments, drawn by gravity over billions of years. Computer simulations show this structure forming naturally from tiny quantum fluctuations amplified by cosmic expansion. Throughout this cosmic evolution, from quantum seeds to galaxy superclusters, the speed of light sets the maximum rate at which structures can grow and influence each other. Quantum scarring, discovered in 2018, shows that certain quantum systems don't thermalize as expected, but instead return periodically to their initial states. These quantum many-body scars represent special trajectories through quantum state space that resist thermalization. Even these exotic quantum phenomena respect the light speed limit for how quickly correlations can spread through the system. The universe's speed limit applies even to the most unusual quantum dynamics. The cosmic neutrino background, released just 1 second after the Big Bang, fills the universe with about 300 neutrinos per cubic centimeter. These relic neutrinos, far older than the cosmic microwave background, carry information about the universe's first second, but they're incredibly difficult to detect because they barely interact with matter. If we could detect them, they would confirm that neutrinos, despite their ghostly nature, have always respected the cosmic speed limit throughout the universe's history. The false vacuum hypothesis suggests our universe might exist in a metastable state, like a ball perched on a shelf rather than the floor. If true, a quantum fluctuation could trigger vacuum decay, converting space to a lower energy state. This bubble of true vacuum would expand outward at exactly light speed, rewriting the laws of physics as it goes. Nothing could outrun it or send a warning because the destruction itself would propagate at the maximum possible speed. The cosmic speed limit means that if vacuum decay started in a distant galaxy, we'd have millions of years before it reached us, but no way to see it coming. Modified theories of gravity like MOND attempt to explain galactic rotation curves without invoking dark matter. These theories modify how gravity behaves at extremely low accelerations, below about 10 to the negative 10 meters per second squared. But even these radical modifications must respect the speed of light. Gravitational influences in MOND still propagate at light speed, and the theory reduces to Einstein's relativity in appropriate limits. No successful theory of gravity has ever violated the cosmic speed limit. The quantum Cheshire cat effect, demonstrated experimentally in 2014, shows that quantum particles can be separated from their properties. In carefully designed experiments, a neutron's magnetic moment can appear to travel along a different path than the neutron itself. This seeming impossibility is another quantum paradox, but it doesn't enable faster-than-light communication. The full quantum state, including all correlations, still respects causality and the universal speed limit. Gravitational memory effects show that passing gravitational waves permanently change the relative positions of objects. After the wave passes, objects don't return to their original configuration. Spacetime itself remembers the wave's passage. This memory is encoded in subtle correlations that propagate at light speed. Even the universe's memory of past events is constrained by the cosmic speed limit, creating a kind of gravitational archaeology limited by light travel time. The quantum Hall effect reveals that electrons in certain materials organize into incompressible fluids with quantized conductance. Edge states in these systems can appear to transmit information instantaneously along the boundary, but careful analysis shows this is due to pre-existing correlations, not faster-than-light signaling. Nature seems infinitely creative in producing phenomena that approach but never violate the speed limit. Sonic black holes in Bose-Einstein condensates provide laboratory analogues for studying Hawking radiation. In these ultra-cold atomic systems, the speed of sound plays the role of light speed, creating acoustic event horizons. Quantum fluctuations near these horizons produce phonons, quantum sound particles, in exact analogy to Hawking's prediction for real black holes. These experiments confirm that the physics of horizons depends on having a maximum propagation speed, whether it's light or sound. The three-body problem in general relativity becomes even more complex than in Newtonian gravity, because gravitational influences propagate at finite speed. When three massive objects orbit each other, each one responds to where the others were, not where they are now. This retardation effect, combined with chaotic dynamics, makes long-term predictions impossible. The speed limit introduces fundamental unpredictability into gravitational systems. Photon spheres around black holes mark where light can orbit in unstable circles. At 1.5 times the event horizon radius, photons can briefly orbit before spiraling inward or escaping to infinity. These spheres define the inner edge of black hole shadows seen by the Event Horizon Telescope. The existence of photon spheres depends critically on light having a finite speed. Without the speed limit, the whole concept of orbital dynamics around black holes would collapse. The Penrose process allows energy extraction from rotating black holes by exploiting frame dragging effects. Particles entering the ergosphere, the region where spacetime itself is dragged around faster than light relative to distant observers, can split, with one part falling into the hole and the other escaping with more energy than the original particle. This seems like free energy, but it actually comes from the black hole's rotation. The process respects all conservation laws and cannot be used for faster-than-light travel. Axions, hypothetical particles proposed to solve the strong CP problem in particle physics, might compose part or all of dark matter. If they exist, axions would be incredibly light and weakly interacting, forming a cosmic field that oscillates at a frequency determined by their mass. Even these ghostly particles would respect the speed of light, with axion field disturbances propagating at or below light speed depending on their kinetic energy. The reheating epoch after inflation transformed the inflaton field's energy into ordinary matter and radiation. This process, occurring around 10 to the negative 32 seconds after the Big Bang, had to respect causality and the speed of light, even as it filled the universe with hot particles. The details of reheating remain mysterious, but any successful model must explain how energy redistribution occurred without violating the cosmic speed limit. Conformal cyclic cosmology proposed by Roger Penrose suggests our universe undergoes infinite cycles, with each cosmic aeon ending in an infinitely expanded state that becomes the Big Bang of the next cycle. Even in this eternal cosmology, each aeon respects the speed of light. Information from previous aeons might be encoded in subtle patterns in the cosmic microwave background, but it would still have propagated at light speed through each cycle. The quantum backflow effect shows that particles can sometimes move opposite to their momentum's direction. A quantum particle with purely positive momentum can have negative probability current, appearing to flow backward. This counterintuitive phenomenon emerges from quantum interference but doesn't violate relativity. The particle's group velocity, carrying energy and information, still respects the speed limit even when probability flows backward. Traversable wormholes in higher dimensions might be easier to create than in our familiar four-dimensional spacetime. Extra dimensions could provide the exotic matter needed to prop open a wormhole's throat. But even these higher dimensional shortcuts would face the same fundamental obstacles. Quantum effects would likely destabilize them, and they couldn't be used to violate causality without creating paradoxes that physics seems designed to prevent. The photon ring around black holes consists of light that has orbited multiple times before escaping. Each successive orbit creates a thinner, dimmer ring exponentially close to the photon sphere. These nested rings encode information about the space-time geometry near the horizon. Future telescopes might resolve this structure, providing a new window into strong field gravity. But recovering this information still requires waiting for photons that respect the universal speed limit. Dynamical dark energy models suggest the cosmic acceleration might vary over time rather than being constant. If dark energy evolves, the fate of the universe becomes uncertain. It might accelerate forever, decelerate, or even collapse. But regardless of dark energy's nature, its effects propagate at light speed. We see distant supernovae as they were billions of years ago, their light carrying information about past expansion rates limited by the cosmic speed barrier. The quantum monogamy principle states that entanglement cannot be freely shared. If two particles are maximally entangled, neither can be entangled with a third particle. This principle, fundamental to quantum information theory, helps explain why entanglement can't be used for faster-than-light communication. The correlations are exclusive and cannot be amplified or broadcast, maintaining consistency with relativity. Fermi bubbles, giant gamma-ray emitting lobes extending above and below our galaxy's center, showcase relativistic particle acceleration on cosmic scales. These structures, spanning 50,000 light-years, were inflated by jets from our galaxy's central black hole millions of years ago. The bubbles expand at significant fractions of light speed, but never exceed it. They're cosmic laboratories for studying how matter behaves when pushed to nature's ultimate limit. The Sunyaev-Zeldovich effect occurs when cosmic microwave background photons scatter off hot gas in galaxy clusters, shifting their energy. This effect allows astronomers to detect clusters billions of light-years away and measure their properties. The photons carrying this information travel at light speed, taking billions of years to reach us. Each observation is a glimpse into the past, limited by the finite speed of light. The cosmic coincidence problem asks why dark energy and matter have comparable densities today when they scale so differently with cosmic expansion. Matter density decreases as the universe expands, while dark energy density remains nearly constant. For most of cosmic history, one or the other dominated completely. We happen to live in the brief epoch, lasting perhaps a few billion years, when they're comparable. This coincidence might hint at deeper physics connecting matter, dark energy, and the cosmic expansion rate, all governed by light-speed causality. Quantum teleportation, despite its name, doesn't actually transport matter faster than light. Instead, it transfers a particle's quantum state to another particle that might be far away. The process requires classical communication to complete, ensuring no information travels faster than light. Scientists have teleported quantum states across thousands of kilometers, but always respecting the cosmic speed limit. The universe allows instant correlations but not instant communication. The Mach principle suggests that local physics is determined by the distribution of matter throughout the universe. Your resistance to acceleration, inertia, might arise from your relationship to distant galaxies. If true, this would mean that local physics depends on cosmic structure, but even this deep connection would respect light speed limits. Changes in distant matter distributions could only affect local physics after light had time to carry the gravitational influence. Quintessence, a hypothetical form of dark energy that varies over time and space, could explain cosmic acceleration without Einstein's cosmological constant. Unlike the static vacuum energy of lambda CDM cosmology, quintessence would be a dynamic field rolling down a potential energy hill. But even this exotic field would respect relativity. Quintessence fluctuations would propagate at or below light speed, and their effects on cosmic expansion would ripple outward at the maximum causal velocity. The trans-Planckian censorship conjecture suggests that quantum gravity effects prevent us from ever probing length scales smaller than the Planck length. Any attempt to concentrate enough energy to probe such scales would create a black hole, hiding the quantum foam from observation. This natural censorship mechanism depends on the speed of light. It's the relationship between energy, gravity, and the maximum propagation speed that creates event horizons protecting nature's smallest scales. Gamma-ray bursts, the universe's most luminous explosions, showcase matter pushed to the extreme. In these cosmic cataclysms, jets of material blast outward at 99.999% of light speed. The incredible energies involved, more than the Sun will emit in its entire lifetime, released in seconds, still can't break the universal barrier. Time dilation in these jets is so extreme that seconds in the jet frame correspond to minutes in our frame. The Blandford-Znajek mechanism explains how black holes can launch these powerful jets. Magnetic field lines threading the event horizon can extract rotational energy from the black hole itself. This process, observed in quasars and active galactic nuclei, accelerates particles to near light speed. But even when powered by black hole rotation, one of nature's most efficient energy sources, nothing breaks the cosmic speed limit. Chronometric cosmology uses precise atomic clocks to test relativity and probe dark matter. By comparing time flow at different heights in Earth's gravitational field, scientists can measure space-time curvature with extraordinary precision. These experiments confirm that gravity affects time exactly as Einstein predicted. The speed of light emerges as the conversion factor between space and time, determining how much clocks slow in gravitational fields. The double pulsar system J07373039 provides the most stringent tests of general relativity in strong gravitational fields. Two neutron stars orbit each other every 2.4 hours, each spinning rapidly and emitting radio beams. This cosmic laboratory has confirmed gravitational wave emission, geodetic precession, and other relativistic effects to better than 0.05% precision. The system loses energy through gravitational waves traveling at light speed, causing the orbit to shrink by 7 millimeters per day. Fuzzy dark matter, consisting of ultralight particles with masses around 10 to the negative 22 electron volts, would have quantum wavelengths comparable to galaxy sizes. This form of dark matter would behave like a vast quantum field, with wave interference creating soliton cores in galaxy centers. Even these galaxy-sized quantum waves would respect the speed limit, with disturbances propagating at or below light speed through the cosmic dark matter field. The ekpyrotic universe scenario proposes that our Big Bang resulted from a collision between higher dimensional membranes. In this cyclic cosmology, universes repeatedly collide, bounce, and expand. Each cycle resets the universe while preserving some information from previous cycles. But even brane collisions must respect causality. The collision front propagates at light speed across the higher dimensional space, ensuring cause precedes effect, even in the multiverse. Superradiance allows rotating black holes to amplify certain waves, extracting energy from the hole's rotation. Waves with specific frequencies can enter the ergosphere, split into positive and negative energy components, and emerge with more energy than they started with. This process could create black hole bombs if the waves were confined, building up exponentially. But even superradiant amplification respects all conservation laws and cannot enable faster-than-light phenomena. The Casimir-Polder force between atoms and surfaces arises from quantum vacuum fluctuations. This force, measured precisely in laboratory experiments, depends on the finite speed of light. If light traveled infinitely fast, the force would vanish. The speed of light thus determines not just cosmic structure, but also the quantum forces between atoms and materials. It's woven into physics at every scale, from subatomic to cosmic. Magnetic monopoles, if they exist, would be topological defects from the early universe carrying isolated north or south magnetic charge. Despite decades of searches, none have been found. Their absence might be explained by inflation, which diluted their density to unobservable levels. If discovered, monopoles would respect the speed limit like all particles. Their magnetic fields would propagate at light speed, and the monopoles themselves could never exceed this cosmic barrier. The lithium problem in Big Bang nucleosynthesis remains unsolved. Observations show about 3 times less lithium-7 in old stars than theory predicts. Various solutions have been proposed, from new physics during nucleosynthesis to stellar destruction of lithium. Whatever the answer, it must respect the causal structure of the early universe. Nuclear reactions proceeded at rates limited by particle velocities, which even at 10 billion degrees were well below light speed. Topological quantum computers might use anyons, exotic quasi-particles that exist only in 2 dimensions, to perform calculations immune to certain errors. When anyons are exchanged, their quantum state changes in ways that depend only on the topology of their paths. This topological protection could enable stable quantum computation, but even these exotic quantum systems respect relativistic limits. Information encoded in anyonic states still propagates at or below light speed. The final parsec problem asks how supermassive black hole pairs in merging galaxies overcome the last parsec of separation to merge. Dynamical friction from surrounding stars becomes inefficient at small separations, potentially stalling the merger. Gravitational waves eventually take over, causing the final in-spiral. This process, playing out over millions of years, showcases how even galaxy-scale events are governed by light-speed propagation of gravitational effects. Vacuum decay could theoretically be triggered by high-energy particle collisions, leading some to worry about particle accelerator safety. But cosmic rays routinely create collisions far more energetic than any human accelerator, and the universe still exists. If vacuum decay were possible, it would propagate outward at light speed from its initiation point. The cosmic speed limit ensures that even universe-ending catastrophes respect causality. The arrow of time itself emerges from the second law of thermodynamics. Entropy always increases. But why does time have a direction at all? The answer connects deeply to the speed of light. In a universe without a maximum speed, causes and effects could be scrambled, past and future would lose meaning. The speed limit ensures that influence flows in one direction, from past to future, creating the temporal order we experience. Every moment of your life, every memory you form, depends on this cosmic conspiracy between light speed and time's arrow. Loop quantum cosmology, applying quantum gravity to the entire universe, suggests the Big Bang might have been a big bounce. A previous universe could have contracted down to quantum scales, then rebounded into our expanding cosmos. Even this radical reimagining respects the speed limit. Information from the previous universe, if any survived, would be encoded in correlations that traveled at light speed through the bounce. We might be living in a phoenix universe, reborn from the ashes of its predecessor, but still bound by the same eternal limits. The cosmic web's filamentary structure reveals how dark matter scaffolds the universe. Ordinary matter flows along dark matter highways, pooling where filaments intersect to form galaxy clusters. This vast network, spanning billions of light-years, grew from quantum seeds through gravitational instability. Every connection in this web formed at light speed or slower. The universe's largest structures are woven by forces that crawl across cosmic distances, never exceeding nature's fundamental limit. Primordial black holes, if they exist, formed from extreme density fluctuations in the universe's first second. These ancient black holes could explain some or all dark matter. Stephen Hawking showed that small black holes evaporate through quantum radiation, with temperature inversely proportional to mass. A black hole with the mass of a mountain would be white-hot, evaporating in a burst of gamma rays. But even Hawking radiation respects the speed limit. It propagates outward at light speed, carrying away the black hole's mass energy drop by drop. The measurement problem in quantum mechanics asks how and when quantum superpositions collapse into definite states. Various interpretations, Copenhagen, many worlds, objective collapse, offer different answers, but all must respect relativity. In relativistic quantum field theory, measurements in one location cannot instantly affect distant particles. The universe maintains consistency between quantum mechanics and relativity through subtle correlations that never enable faster-than-light signaling. Cosmic variance limits our knowledge of the universe's largest scales. We can only observe one universe from one location, making statistical statements about the biggest structures uncertain. It's like trying to understand Earth's geography from a single photograph. This fundamental limit intertwines with light speed. We see distant regions as they were in the past, and some regions are forever beyond our horizon. The universe keeps some of its secrets through the conspiracy of finite speed and finite time. The phantom energy hypothesis suggests dark energy might have an equation of state parameter less than -1. Such exotic energy would cause ever-accelerating expansion, eventually tearing apart galaxies, stars, planets, and even atoms in a Big Rip scenario. The speed of light would determine how this cosmic doomsday unfolds. The destruction would propagate outward at light speed as space itself becomes unstable. Even the universe's potential end must respect its fundamental speed limit. Time loops in general relativity, while mathematically possible, face the grandfather paradox and other causality violations. The Novikov self-consistency principle suggests only self-consistent loops could exist. Events would conspire to prevent paradoxes. But maintaining consistency might require infinitely precise coordination of events. The universe seems to prefer simpler solutions, no time loops at all. The speed of light works with other principles to maintain a sensible flow of cause and effect. The quantum Zeno paradox becomes even stranger in relativistic systems. Continuous observation can freeze a quantum system's evolution, but in relativity, simultaneous observation becomes frame-dependent. Different observers disagree on when measurements occur. Resolving this paradox requires careful consideration of how measurements propagate at light speed through quantum fields. Even the act of observation must respect cosmic speed limits. Warp drive metrics in general relativity show that faster-than-light travel might be geometrically possible, but physically impossible. The Alcubierre metric requires negative energy densities that likely don't exist. Recent research shows that gathering enough exotic matter would collapse into a black hole before forming a warp bubble. Every loophole physics seems to offer for FTL travel comes with a catch that preserves the cosmic speed limit. The information paradox extends beyond black holes to the entire universe. In an eternally expanding cosmos dominated by dark energy, all structures will eventually dissolve. Black holes will evaporate, particles will decay, and the universe will approach maximum entropy. All information about our current universe will be effectively scrambled beyond retrieval. But this cosmic forgetting will proceed at light speed, taking Googles of years to complete. Boltzmann brains, random fluctuations producing conscious observers, become paradoxically more likely than evolved life in the far future. In an empty universe near maximum entropy, random quantum fluctuations could occasionally create thinking beings. This unsettling possibility suggests our universe might be fundamentally unstable, or that our understanding of probability in cosmology needs revision. But even Boltzmann brains would be constrained by light speed, their thoughts limited by how fast neural signals could propagate. The holographic bound limits information content to surface area rather than volume. A sphere 1 meter across can contain at most 10 to the 70 bits of information, far less than classical physics would suggest. This bound, emerging from black hole thermodynamics, might reflect deep properties of quantum gravity. Information itself might be the fundamental entity, with space, time, and matter emerging from information theoretic relationships limited by light-speed causality. As we stand at the shore of knowledge gazing into the cosmic ocean, the speed of light emerges not as an arbitrary limit, but as the fundamental heartbeat of reality itself. It's the rate at which the universe computes its next moment, the maximum speed at which cause can create effect. From the quantum foam at the smallest scales to the cosmic web spanning billions of light-years, this universal constant shapes everything we see and everything we are. You are made of atoms forged in stellar cores, their particles bound by forces that propagate at light speed. Your thoughts emerge from electrical signals crawling along neurons at a mere 100 meters per second, glacial compared to light, but still governed by the same electromagnetic laws. When you look at stars, you're seeing the universe's history written in light that has traveled for years, centuries, or eons to reach your eyes. You are, in a very real sense, a collection of cosmic history assembled by forces limited by the universal maximum speed. The speed of light connects the impossibly small to the incomprehensibly large. It appears in the equations governing subatomic particles and in the mathematics describing the universe's expansion. It's not just a speed, it's the fundamental ratio that connects space to time, energy to mass, and cause to effect. Without this cosmic speed limit, the universe would be a chaos of uncaused effects and impossible paradoxes. Perhaps most profound is what the speed of light teaches us about our place in the cosmos. We are not separate from the universe, but woven into its fabric by the very forces that set its limits. The atoms in your body, the thoughts in your mind, the ground beneath your feet, all are connected by a vast web of causality spreading outward at 299,792.458 kilometers per second. As you go about your day, remember that you're participating in a cosmic dance choreographed by the speed of light. Every atom in your body respects this limit. Every force you feel propagates at this speed. Every star you see shines with light that has traveled through space at this universal constant. You are not just an observer of the universe. You are the universe observing itself, bound by the same beautiful, inexorable laws that govern galaxies and quarks alike. The next time you switch on a light or see the sun break through clouds, take a moment to marvel at the profound mystery you're witnessing. That light carries with it the fundamental speed limit that makes the universe possible, a limit that ensures causality, enables existence, and weaves space and time into the magnificent tapestry of reality we call home. In understanding why nothing can exceed the speed of light, we glimpse the deep mathematical poetry written into the cosmos, a poetry that includes us as both readers and verses in the grand cosmic story. If you are still watching, make sure to subscribe to the channel and give a thumbs up. Your support is my biggest fuel to keep motivated. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. Why traveling at the speed of light could destroy the universe. In this video, we explore the terrifying consequences of breaking the ultimate cosmic speed limit. See you there.